João, tá me
Oi?
escutando? Como é que vocês estão aí? Sararam?
Graças a Deus, tudo bem.
E as crianças?
Também. Nossa, graças a Deus,
Maravilha.
hoje voltaram para a escola.
Já voltaram?
É.
O treinador da minha academia fechou a academia essa semana.
Ah, é?
É, ele pegou. Bom, mas eu nem tô lá, né? Então eu nem ia treinar mesmo. Mas coisa
Entendi.
parou, né? Mas beleza. Bom que vocês estão em ordem aí. Abraço.
Mas graças a Deus está tudo bem, mas credo, foi punk,
Assusta,
né?
né? Mas passou. Graças a
Passou,
Deus.
graças
Até
a
mais.
Deus. Bom dia, Humberto. Bom dia, pessoal. Tudo bem?
Bom dia, João. Bom dia a todos.
Eu já acostumei. Bom dia. Good morning. Buenos dias, José Luiz. Tudo bem? João, eu que vou ser o seu chairman, viu?
Ok.
It's my pleasure to introduce Professor João Carlos Ferreira Costa from IBILSE UNESP, São José do Rio Preto. He is going to talk about the topological classification of circle-valued Morse-Bott functions. Thank you very much for your talk, João.
Okay, thank you, Marcelo. Good morning, everyone. First, I would like to thank the organizer for this opportunity. For me, it's a great pleasure to be here, even if in a virtual way, okay? I congratulate the organizer for this very nice event. Thank you. The title of my talk is on the topological classification of circle-valued Morse-Bott function. This is a joint work with Érica Batista from Universidad Federal do Cariri e Ingrid Mesa Sarmiento from Universidade Federal de Itajubá. I would like to thank the FAPESP and CAPES by the financial support of this work. Well, what's the main goal of this work? The main goal of this work is to investigate the topological classification of circle-valued Morse-Bott function from M2 to S1 up to topological conjugacy, where M2 is a closed connected orientable two-manifold, a surface. We present a complete topological invariant, which is a graph, called here MB-Hib graph. And in the last part of the talk, I introduced the problem of realization of a graph in the special case when M2 is the standard sphere M2, S2. This talk is based on two papers. The first paper is dedicated to sphere, and it was published in Journal of Singularities in 2018. And now we generalize some of the results, and we have a preprint submit to publication for the general case where M2 is a closed connected orientable surface. To understand this goal of this talk is we need to understand the meaning of four ingredients here. What are Morse-Bott function? Why do we study circle-valued case? What does topological conjugacy means? And how can we define this graph MB-Hib graph? After we introduce these four ingredients, I present our main results, okay? Then the first ingredient is the Morse-Bott function. Morse-Bott function is a generalization of the definition of Morse function. They are introduced by Bott in 1972. And the difference is that the critical set of F is formed by points, but also by smooth submanifolds with different dimensions. These submanifolds are called non-degenerate singular submanifolds. Let's define them. Here we consider M just a m-dimensional manifold and F a smooth function. A smooth submanifold S in the singular set or critical set of F is a non-degenerated singular submanifold of F if S has no boundary, S is compact and connected, and for all P in S, the Hessian of S restricted to the normal space to S is non-degenerated. In other words, for all P in S, the Hessian of F in a normal direction is a Morse function. This is definition of non-degenerate singular submanifolds. Okay, and a Morse-Bott function is a function f where the singular set consists of isolated points and non-degenerate singular submanifolds. Okay. Analogously to the Morse case, when we study Morse-Bott functions, we have also a Morse-Bott lemma, similar to Morse lemma. A Morse-Bott lemma said how is the how f can be expressed in local coordinates. Okay, and we have this expression of f in local coordinates in a neighborhood of p, where p is in S, where S is a connected component of the singular set of F. And the dimension of F is K. Then here we have this expression. We observe that if K is equal to 0, then we have exactly the Morse lemma, the classical Morse lemma, okay? Some examples of Morse-Bott function. The first example, the Morse functions are Morse-Bott functions with isolated singular points. Then, in this case, the submanifolds, the critical submanifolds, have dimensional 0. Okay. The second example, take f x, y, z given by minus x squared plus y squared. This is a Morse-Bott function. This follows from Morse-Bott lemma. This have this characterization. And f is not Morse in this case. Morse-Bott functions appear in several contexts. For instance, they appear in nuclear physics when we study Wigner's functions. Here I present a graph of a kind of Wigner function. More details about Wigner functions can be found in the papers of reference of this talk. Here we have isolated singular point here, and we can look 3 S1 critical submanifolds, submanifolds of dimension 1. Okay. But here in this work, M2 is a two-dimensional closed manifold orientable. Okay. Then the singular submanifolds in our case can be divided in 3 types. The singularities are maximal or minimum points, which are extrema points of F and isolated points. Saddle points, which also are isolated singularities, and singular circles. Singular circles are points in singular submanifolds which are homomorphic to S1. On these circles, the function assumes extremal values. These are the possibilities of the singular set or in this submanifolds non-degenerate singular in the singular set of F. The second ingredient is to understand why consider this kind of function, why consider circle-valued Morse-Bott function. The global properties of circle-valued Morse-Bott function are quite different from classical Morse-Bott function, taking values in the line. For instance, there is example of circle-valued Morse-Bott function from torus to S1 with no critical points. For example, if we consider a torus T2 and S1 here, and we consider the radial projection, each circle like this can be projected on S1 by a function, for instance, f, such that alpha beta point of this circle, I project in alpha, for instance. This function has no critical points. Okay? And this situation is different from classical Morse-Bott function taking values in R, in the line, because in the line, the function has at least two critical points. But we have the following result when we consider simple Morse-Bott function. Simple here means that f has only one non-degenerated critical submanifold for each level curve of f. And if the Euler characteristic of M is non-zero, then in this case, yes, f is always singular. Okay. Another motivation to study circle valued Morse-Bott function goes from singular theory. And when we study the topological classification of finitely determinate map germs from R3 to R2 with isolated zero, the topological type of these guys is determined by the link of F. And in this case, the link is a circle valued function from S2 to S1. This was the first motivation for me to study circle valued Morse functions and after Morse-Bott functions, okay? And how is the definition of circle valued Morse-Bott function? These functions are just locally Morse-Bott function. We have the following definition. A function f is called a circle valued Morse-Bott function if for any x in M2, we can choose a neighborhood V in S1, a neighborhood of fx, and we consider a diffeomorphism phi in the line. And when we look locally, this map phi composed to f, we have a real valued Morse-Bott function. Then this is the locally Morse-Bott function, okay? This is the definition of circle valued Morse-Bott function. Some example. The first example, we have f from S2 to S1, S2 the standard sphere, f given by the radial projection, as in the picture. In this case, we have maximum and minimal points, like this, and a saddle point, like this. In fact, this example is a Morse function, in particular Morse-Bott function, okay? Another example, consider M2 the B torus and F the radial projection from B torus to S1, like in this picture. In this example, we have a circle valued Morse-Bott function with two saddle points and two S1 critical circles, okay? This is one example of circle valued Morse-Bott function in the B torus. The third ingredient, what kind of topological classification are we interested in? We introduce a notion of equivalence in a natural way. In singularity theory, the most natural equivalence between two maps is the A equivalence or topological A equivalence given by change of coordinates in the source in the target of the maps. Here we have the definition of C0 A equivalence. But here we do a little bit modification because we require that H, the homeomorphism H from M2 to M2, we want that it sends singular fibers to G into singular fibers of F because we want to preserve the topological types. And if we consider any homeomorphism, H could send a singular fiber in a regular fiber. And this is not interesting. Then we include this hypothesis about H. And about K, K is the change of coordinates in target, S1. We required that K preserves orientation. This hypothesis also appears in Morse classification. It's necessary to order the critical values of F. Then this equivalence relation is the most natural in such sense. And the last ingredient of my talk is MB-RIB graphs. First, why we look for a graph as an invariant? Graphs are simple objects to study, to work. It's simpler than algebraic invariants, for example. Then it's very interesting to define an invariant as a graph, okay? To define MB-RIB graph, first we start reminding which are classical RIB graphs. The RIB graphs were introduced by RIB to study Morse functions on closed manifolds. More generally, RIB graphs can be defined for continuous function, defined on topological space. The definition is the same. RIB graph is a quotient space given by contracting the connected components of the little curves of the set to points. Right? Like this example, consider here f the eigen function, and we contract each level curve to a point. Okay? Here is a saddle point. We contract here. Here we have 2. We contract here. Okay? One more example. This is a RIB graph. Here we have maximal and minimal points and several saddle points. An interesting remark is that RIB graph is not always a finite graph. This is interesting. But when we consider a smooth function defined on closed manifold with a finite number of critical values, then Sayek showed that this quotient space is homeomorphic to a finite graph. In this situation, we have a finite graph. And here in this work, we consider simple Morse-Bott function, and we introduce a graph, but a graph with more additional extra information than the classical RIB graph. Here, we call this our graph by MB-RIB graph. Simple here means that F has only one non-degenerated critical submanifold for each level curve, okay? To define our graph, first we introduce the following equivalence relation on M2. X is equivalent to Y if and only if they have the same image, and X and Y are in the same connected component of F-1 of Fx. Then, if we have F from M2 to S1, a simple Morse-Bott function, the quotient space M2 to this equivalence relation, which we denoted by RF, admits the structure of connected graph in the following sense. The vertices of this graph are the connected components of level curves of critical level curves, and each edge is formed by points that correspond to connected components of regular level curves. Here we have a difference of classical Hibby graph, because in general, in classical Hibby graph, it's required that the critical level set in the definition of the vertices contains the critical point. But here, we not have this condition. Then, because one can be appear regular vertex in our graph. Each vertex of the graph obtained as in the previous proposition can be of four types. Then we have these four types of vertex of the graph. Here we have a saddle point. Here a maximal point, or analogous to minimal point, is the extremal vertex in the graph. Here we have a regular vertex, and here we have a vertex related to S1 critical or singular circle. And here the vertex associated to critical circles we denote by white vertex. Then in our graph we have two possible colors of the vertex. Okay. But to define our graph, we need one more information. And this information is related to the topological classification of aids on closed orientable surface. This is very important because if you want to obtain a global invariant, to do this, we start from a local study. Then it's necessary to analyze the critical fibers, especially saddle points and S1 critical submanifolds in our case. Since we are in the two-dimensional manifold, we need to know how the saddle appears in the surface. We need to distinguish two saddle points. And this classification of eights because a saddle, we can look locally a saddle point like this. We have a saddle point and two separatrix, and we can and when we can the closure, we have an H. Then it's important to know the topological type of H. An H like this can be seen as an immersion of S1 in M2. And the classification of H's in M2, where M2 is a closed orientable surface, was done by Ingrid Mesa Sarmiento, Regilene Oliveira, and José Martínez Alvaro. And this classification plays a key role to define our MD-Hibby graph. In fact, these authors also classify the circles in orientable closed surface. But this information is not necessary to define our graph because this information it is contained in the information given by the Hibby graph. Okay. Then it's just necessary to know about the topological classification of aids. And how we can to distinguish two saddle points. Then we consider, for instance, a singular fiber contain a saddle point, like in this picture. Okay. We call this curve a saddle curve. We observe that if we consider a neighborhood, a regular closed neighborhood of B, like this is a neighborhood of B. This neighborhood is homeomorphic to a sphere minus 3 disks. So we have 3 boundary curves in this neighborhood. maybe it's better to look in this picture when we have a saddle point and we take a neighborhood. We have three boundary curves, and one of these boundary curves is contractile to the saddle curve. In this case, this curve is contractible to the. It's difficult to draw in this slide. Sorry, or in this picture, this curve, this boundary curve, is contractible to the saddle curve, and we call this curve JB. And another curves, and this is JB, and another curve is JS. Okay. Then let's see the function which associate each saddle vertex to the graph to the edge that contains the JB curve. Then here in this case, the JB curve is this. It is contractible to the saddle curve, and then we associate to this edge a symbol star to identify this property of this saddle. Okay. Now we can to define our graph. Let V1, VR in S1, critical values of F. We choose a base point V0 in S1, and we choose an orientation of S1. We can assume that the critical values are ordered, and we label each vertex with the index I, if it corresponds to critical value Vi. Then the graph given by vertices and edges like defined in RF definition, together with the labels, colors of the vertex, and the function C, this graph is called here MB graph associated to a simple circle valued function from M2 to S1. And we denoted it by gamma F. And this is our graph. We observe that if M2 is equal S2, there is only one topological type of edges of saddle curves. Then it's not necessary to label the edges that contain the JB curve. Then the graph is not necessary to put the symbol star in this case. But when M2 is different to S2, is necessary this more information. Moreover, if M2 is equal to the standard sphere, the MB graph is simple, is a tree. We proved this in our first paper. Here we have some example. Consider f and g from S2 to S1 to Morse-Bott function given by the radial projection. Here we have the MB graphs associated to f and g respectively. We observe that F1, that f and g have the same classical Hib graph. If you draw the same classical, if you construct the classical Hib graph, they are the same, but our MB Hib graph are distinct because we have different number of vertices. Moreover, F is not surjective map, and G is a surjective map. Then they are not topologically equivalent. In particular, they are not topologically conjugated. This shows that the classical Hib graph is not sufficient to distinguish these two kinds of Morse-Bott function. Okay? just the classical Hibby graph is not sufficient to distinguish because they have the same Hibby graph, but they are not topological conjugated. The second example, we consider simple Morse-Bott function defined on the torus, taking values in S1. And here we put the respective MB-Hibby graphs, as in the picture. Note that without the symbol star in the edge, the graphs are the same. Then, but if we consider MB-Hibby graphs, including the star in the respective edge associated to the topological type of saddle, which is associated to JB curve, then the MB-Hibby graphs are different, okay? Because the topological type of the saddle curve are not the same. Then here it's important to emphasize the role of star in the edge of the MB-Hibby graph, okay? Comparing MB-Hibby graph and classical Hibby graph, the MB-Hibby graph was inspired in the invariants introduced by Érica Batista and Ingrid Sarmiento in their PhD thesis. Our MB-Hibby graph contains some extra information than their graphs. In fact, our graph here has vertices correspond to the regular connected components of critical values set, and white vertex correspond to the singular circles, and distinct topological type of saddle curves, which is determined by symbol star in the corresponding edge of the graph, okay? When we look at F, and F is not surjective, then F may be regarded as a simple Morse-Bott function taking values in the line via stereographic projection. And in this particular case, we can apply the results of Ingrid Sarmiento, Regilene Oliveira, and José Martínez Alvaro. It's obvious that the labeling of vertices is not uniquely determined, since it depends on the chosen orientation and the base point. Then different choice will produce either a simple permutation or inversion of the labeling in MB-Hibby graph. This allows to introduce a notion of equivalence between MB-Hibby graph. Then we can say that two MB-Hibby graph is equivalent if there exists graph isomorphism, J and L, J preserving the assignment of the function C, and such that this following diagram is commutative. Isomorphism here means a bijection between the set of vertices, which adjacent vertices are taken in correspondent adjacent vertices. PF is the set of vertices, and delta F is the discriminant set of F. Then we have our main result. We prove that MB-Hibby graph is a complete topological invariant. First, we prove that if F and G are topologically conjugated, then their respective MB-Hibby graphs are equivalent. This side is easy because from the definition of topological conjugacy, the homeomorphism induces the graph isomorphism from the definition of equivalence of graph, then it is. But the converse is not easy, is more difficult. If you have two graphs equivalent, then F and G are topologically conjugated. This is a very nice proof. We can find this proof in our second paper in the reference. And an example, the two simple Morse-Bott considered in example 1 are not topologically conjugated, since their respective Morse-Bott Hib graph are not equivalent. Then here, these maps are not topologically conjugated because their MB-Hib graph are not equivalent. The number of vertices are distinctive. More, if we do not consider regular vertices in the MB-Hib graph associated to F and G, then this graph would become indistinguishable and hence equivalent. However, the functions F and G are clearly not topologically conjugated. Then it's very important the regular vertices in the MB-Hib graph. And the last part of my talk, we introduce a problem of realization of graph problem, a realization of a graph problem. When is a finite graph the MB-Hib graph of circle-valued Morse-Bott function? This is an interesting problem. Recently, other people are also investigating similar questions about realization of graph associated to the Hib graph. For instance, Sharp, Matsumoto Saeki, Michalak, Diobuk, Ingrid Sarmiento, and other authors. Okay, this is interesting problem. Let us present an answer to this question in a special case when M2 is equal S2. Then we have the following realization theorem. If we consider G be a finite connected Dirac tree, this kind of hypothesis is usual when we are working with the realization of Hib graphs. Then G can be realized as the MB-Hib graph associated to a simple Morse function defined from S2, if only if we have four conditions. The vertices have degree 1, 2, or 3. The vertices of degree 3 have in degree 1 and out degree 2, or in degree 2 and out degree 1. Remember that in degree plus out degree is degree of the vertex. The 3G is any partite graph. This means that the set of vertices can be partitioned into any disjoint independent set. And the fourth condition is about the number of, is related the number of regular vertices. Then it's a realization theorem in the special case where M2 is equal to S2, the standard sphere. Okay. Recently, we are investigating realization problem of graph for other class of manifold, but it's more difficult problem. Okay. Here we have some main reference. The reference 4 and 5 are the cited reference from Ingrid, Regilene Oliveira, and Martins Alvaro. Okay, thank you very much for your attention.
Thank you very much, João, for your talk. I have some few comments and also questions about it. The first you told before in the last page, are you considering, for instance, functions from S3 to S1, for instance, or from S3 to S2, or something in this? Which kind of generalization are you studying in this sense, please?
We study circle valued functions defined from sphere to S1 It's a very interesting problem. I have studied this kind of problem, but the problem is more difficult. We have some results in this direction. But here, first, with respect to the Morse-Bott specifically case, first we are interested in to understand first the two-dimensional case, and after this, the next step is to investigate it. For instance, the three sphere, because this problem can be related to the topological classification of finitely determinate map germs, for instance. Then it's a very interesting problem.
Okay. I have another comment. It's quite funny because we, we talk every week, but not about these things. And I have been following your talks, but there is another way to look to these things. If you consider S1 inside R2, okay, it's a circle inside R2, and if you look to S2 inside R3, you are looking, in fact, a restriction of a map from R3 to R2 that's restricted to S2 and is going to S1, okay? And if you look to a map from R3 to R2, you have some kind of singularities which appear like cusps. And you can always avoid this cusps doing some kind of homotopy. This is a work done by Saek and some of the people that works with him. It's a different point of view, but it's the same. It's quite a elimination of singularities in this case. And when you look to the Morse-Bott functions, but you consider the more general case, maybe you can use these results of SEC to show that you can change any, let's say, stable map germ, stable map from R3 to R2 to obtain a Morse, to do by homotopy or something, a Morse-Bott function. Maybe it could be interesting to show the size of the Morse-Bott functions in this situation. I don't know. Maybe a suggestion.
Yes,
Okay.
yes. The homotopy type of maps from S2 to S1, for instance, this can be associated to the topological contact equivalence.
That was going to be my third question.
Yes, and not the usual topological equivalence, but the topological contact equivalence.
Good. Okay, we can talk later about this. Are there any questions here in the live people? No? And questions in people that is following the talk? No? If there is no question, there are no more questions, so let's thank you, the speaker, again for this very, very nice talk.
Thank you very much. Thank you very much.
João. João, a gente conversa hoje à tarde, tá? Às 2.
Ok.
Next talk will begin at 9:50, okay? Can you see me, Konstantinos? You
Yes,
know
I
who
can
I
see you,
am?
Marcelo. How are you?
I am fine. Very happy to see you. Congratulations
Very
for your
happy.
baby. Maybe it's walking now.
Yes, exactly. Now it's doing mathematics
Doing
now.
mathematics. Go, no, don't do it to him, please, Konstantinos. It's
I didn't
everything
have
nice
any
with you?
choice.
Everything is all right with you and your family?
Everything is great, Marcelo.
Good.
Everything is very nice.
Very nice. Nice
Very
to
happy
see
to
you.
see you all.
It's quite funny because I was not supposed to be the chairman today, but for coincidence, I am the chairman of your talk. It's a great pleasure for me.
For me as well. It is
Yes.
amazing.
Very nice to see you. Very nice.
Very nice to see you too. Should I start? Can you all see me here?
Sorry?
Should I start the presentation? Can you see me here?
Yes, yes. You can present your talk if you prefer, then I begin.
Just to see if we can if you can see me and if you can see the talk.
I
So
see you, but not your presentation yet. Please put the
here
okay. Then I can read
it's
the
okay. Yeah,
name.
perfect.
Great. It's my pleasure to introduce Professor Konstantinos Kourliouros from Greece. Oops, you great. And he's going to talk about the Bruce Robert numbers and weighted homogeneous functions on analytic varieties. Go on, Konstantinos, please.
Thank you very much, Marcelo. So it is great to be here again and see you all again. It is online, of course. It is not the same, but still, it is very nice that it is still happening. Actually, I will talk about a problem which started in Victoria. So it was the previous meeting on singularities and foliations. When Carles Osina, he was presenting some results of his and Sidinia that they had together. And there was this thing that there is this relative Milnor number, as it is said, or Bruce Roberts number. And they calculated the quotient, the Milnor number over the Turina number in this relative case. And I remember now, I asked what happens if this quotient is 1. So this started actually research between the three of us. Some time later, yeah, not in the start of 2019, but sometime later, which is still ongoing with very interesting results, but admittedly a difficult problem, unexpectedly a difficult problem. So now I will present you these results of this joint work. So I will start with history and the motivation of this theory, which has to do with a relative version of Saito theorem. So let us start with ordinary objects that we already know. So we are given a function germ in the analytic category with isolated singularity at the origin. We associate to it very well-known invariants. The first is the Milnor number, which is the dimension of the local algebra of the singularity. Here, theta throughout the text will be the modulo of germs of vector fields at the origin of Cn. And the df of theta evaluated at theta is just a Jacobian ideal, yeah, generated by the partial derivatives of f. So this is the Milnor number as an analytic invariant, and it's also the Turina number, where we add in the Jacobian ideal the ideal generated by the function f itself. These two numbers have very significant interpretations. First of all, the Milnor number is a topological invariant. It is equal to the number of spheres in the bouquet decomposition of a Milnor fiber. Whereas the Turina number is a purely analytical invariant, and it encodes the non-trivial deformations of the isolated hypersurface singularity defined by f. So we will call it y. So this is the minimal dimension of a base of a semi-universal deformation of this hypersurface. Obviously, by definition, we have that the Milnor number is bigger or equal to the Turina number. And the question for which functions we do obtain equality was answered in a famous paper of Kyogi Saito, that equality of the Milnor and Turina numbers of a function is equivalent to the quasi-homogeneity of the function. So to recall what is, I guess everyone knows what quasi-homogeneity of a function is by now, yeah? But let us recall what it means. It means that there exists a coordinate system and positive rational weights, which positive rational numbers, which are called the weights, and one more rational number, which is called the degree of quasi-homogeneity, such that in the expansion of F appear only monomials whose exponents lie in the hyperplane defined by this equation. The sum of the Wi mi equals to D. So you get a hyperplane, a fine hyperplane with the space of all exponents, and all monomials lie on this hyperplane. In a little bit more invariant terms, is equivalent to say that the function f is an eigenfunction of a semi-simple vector field, of a semi-simple derivation with eigenvalue d, and this derivation is usually called, so this chi w is called the Euler vector field of f. Now, of course, Saito's proof is kind of rather trivial. It doesn't use much things. It uses, because you see that equality of Miller and Turina numbers means that there exists a vector field such that the delta f is equal to f, yeah. So as we will see below, in most cases in proof of Saito's theorem, at least in a specific case where multiplicity of f is bigger equal to 3, it is just taking what is called the Poincare-Dulac normal form for this vector field. But anyway, after Saito's proof, or yeah, it was after Saito's proof, this difference had a significant interpretation in terms of the rank homology. It was shown that this difference of the Miller and Turina number was the n-1, the rank homology of a complex of Keller differentials of the hypersurface Y. We don't need it now, but it is just to show that it has a simple interpretation in cohomological terms. The next more difficult and the next step is to consider isolated complete intersection singularities and ask how we can characterize quasi-homogeneity of isolated complete intersection singularities. And this, after Saito's work, was a very, very difficult problem by many mathematicians. So, for example, Wall and Gruel and Steinbrink, every one of them was involved in a way or another with this problem. And there were partial results until 2002, when Henrik Vosegaard proved that any positive dimensional analysis is weighted homogeneous, quasi-homogeneous, if and only if its Milnor number is equal to the Turina number. Here again, the Milnor number is a topological invariant is equal to the number of spheres in the Bouquet decomposition of the Milnor fiber of the ICES. And the Turina number is again the space of deformations, of infinitesimal deformations, non-trivial, of the ICES. Here, of course, I would like to say that in Vosegaard's case, in the case of ICES, it is obvious that we are talking about K equivalence, yes? We're talking about weighted homogeneity under changes of coordinates and other changes of the generators of the ideal defining the ICES. But anyway, the point here is that both in Saito, in the isolated hypersurface case, in the ICES case, the most important point is that the singularities are isolated. In both cases, one uses this fact to produce a vector field with positive rational eigenvalues. And then it is almost immediate that our object will be quasi-homogeneous. In contrast, though, to Saito's proof, Vosegaard's proof, I would say it is infinitely more complicated. You see immediate, I just wrote it down, it doesn't mean that we understand what is written here, but to see what is going on is that this difference of the Miller and Turina number, it is expressed in terms of invariance coming from the link from the mixed structure of the link, the singularity, and also with invariance having to do with the resolution of singularity. So these are called purely elliptic singularity or log canonical or canonical and so on. So the other point is that in Vosegaard's proof, exactly this formula it is used to prove the theorem, whereas in Saito is rather direct. Yeah, you don't need any formula to prove anything. Now, going to the next step, which is even more difficult, because here again we know nothing, is how to characterize quasi-homogeneity of an arbitrary analytic set. By the way, I haven't written it, but an analytic set is quasi-homogeneous if it is invariant under the quasi-homogeneous dilatations, yeah, the origin. So it is the same thing as saying that it has a semi-simple vector field with positive rational eigenvalues, which is tangent to it. It is tangent to the smooth part of X. And here not much is known, but there is a trivial thing that you can say, considering the so-called module of logarithmic vector fields. So these are all vector fields that leave the ideal of functions. The ideal of functions define X, leaving invariant this ideal. Or equivalently, saying that are all vector fields that are tangent to the smooth part of X. And you can write it as a theorem. It has been proved several times in the literature that the only quasi-homogeneity of an analytic set is equivalent to the existence of a logarithmic vector field, so tangent to a smooth part, which has positive rational eigenvalues. And these are, so eigenvalues of a vector field, of course, are eigenvalues of its linear part, yeah? So you take a Jacobian matrix of this vector field. And what is going on now here? So just let me show you how simple it is. You take a vector field and you use this classical theorem from ODEs and you split it in appropriate formal coordinates to semi-simple and nilpointed parts. So you have a semi-simple part which is a diagonal vector field with the eigenvalues here. And the other part is a nilpointed vector field with zero eigenvalues, which commutes with the semi-simple part. And this commutation relation is important. Yeah, so you have formal change of coordinates, and in the formal category, you get this decomposition. But if eigenvalues are positive, then we'll see it is decomposition is an analytic case as well. And then after that, one uses a theorem of César and Wiebe, which is old, but can be proved. It's also proved by some recent papers in 2018 by Niklas Graf using analytic methods, but it is standard. That if you have a vector, an ideal which is invariant under a vector field, then the ideal is invariant both by the semi-simple part and the nilpointed part in concurrent coordinates. So it means that so the first point is that if you have a vector field which leaves an ideal invariant, and this vector field has positive rational weights, then it's the same thing. It's an exercise to show that this ideal admits a system of quasi-homogeneous generators with positive weights. And these all are in formal category, but we can pass to analytic category immediately because the eigenvalues are positive. So they belong, there are no small denominators. There is no problem in passing to analytic category. Now, having said this, you see that for analytic sets, there is almost nothing, yeah? But having said this, I want to generalize and talk about the main problem that we'll be dealing with here is how to generalize this in the relative case, so for stratified isolated singularities. And I will explain. So our aim is to generalize these Saito and Vossegaard theorems for finitely determined function terms on analytic varieties. So this is called Rx equivalence. It means taking functions which are finitely determined with respect to diffeomorphisms, preserving an analytic variety X. I will say what it means in a bit, but apart from this is a classical subject, yeah, starting from the boundary singularities of Arnold and Liasco, and considering afterwards by Bruce and Roberts, all this very nice theory about relative singularities theory, someone would say. These objects appear naturally in physics, yeah, and in mathematical physics and everywhere in control theory, in variational calculus, Lagrangian singularities, time functions, and so on. So this is why, at least in the beginning, this is important in terms of applications. So what is finite Rx determinacy? Means that the function f has finite relative or Bruce Roberts number, as it is usually called. So this is mu x of f, which is thus the dimension of this algebra, where here you see you evaluate df on the module of logarithmic vector fields for x. So the vector fields which are tangent to x. This is the so-called relative Jacobian module. And this means that f defines actually stratified isolated singularity in the classical sense of Le with respect to the so-called logarithmic stratification of x. So logarithmic stratification, not to say much, this is stratification because you see that this module theta x is coherent. It has a Lie algebra structure, so you can use some type of Frobenius theorems, Sussman, and so on. And you see immersed submanifolds or strata. But on the other hand, you can say that it's the same thing as having the canonical stratification of x, and then add one more strata, which is the complement in Cn, yeah. And that's that the function has isolated singularity, stratified isolated singularity, so it is everywhere submersion, except possibly at the origin, yeah. And when restricted in its stratum, of course. So this is our point, to consider objects like this here and see what we can say. So we have the Miller number, and in the same way, we can have a relative Turina number. We call it Bruce Roberts Turina number, which is just adding to the relative Jacobian ideal, the ideal of function, the ideal of f, generated by f. And again, by definition, we have that the Bruce Roberts Miller number is bigger or equal to Bruce Roberts Turina number, and it is natural to ask for which pairs we do have equality. We notice that this equality is equivalent to the function f here belonging in the relative Jacobian ideal, which is exactly equivalent to the existence of a logarithmic vector field, so tangent to x, such that it admits the function f with eigenvalue 1 when you do the derivation, yeah? So this is equality. This motivates the following definition, which we will use throughout. We will say that the pair f comma x, so I recall x is an analytic set, is relatively quasi-homogeneous if there exists a coordinate system such that both the function f and the analytic set x are quasi-homogeneous with respect to the same positive rational weights. Equivalently, it is the same as to ask for existence of coordinate system and the semi-simple vector field with positive rational eigenvalues, which is logarithmic for x, so it is tangent to x, and is Euler for f. So it's the same thing. And we see that if the pair fx is relatively weighted homogeneous, quasi-homogeneous, then f belongs to its relative Jacobian ideal, yeah, because it is obvious the Euler vector field is tangent to x and is Euler for f. So we immediately obtain equality of the Bruce Roberts Miller and Turina numbers. So we make the following conjecture, which is naive because I will disprove it immediately, but it is natural in a way to ask whether the converse also holds. So if we have a relative version of Sato's theorem, which would be formulated as follows. Suppose that we have a pair f comma x with finite Bruce Roberts number, then equality of the Bruce Roberts Miller and Turina numbers is equivalent to the relative quasi-homogeneity of the pair. I repeat, it means that there exists a coordinate system, positive rational numbers, such that both f and x are weighted quasi-homogeneous with respect to the same, exactly these numbers. We also notice and we see that equality of the Bruce Roberts Miller and Turina number immediately implies equality of the ordinary Miller and Turina number of f. So that f is indeed quasi-homogeneous in some coordinate system with respect to positive rational weights by Sato's theorem. But it is easy to construct examples and see that in this coordinate system, the set x might not be quasi-homogeneous. So in the same terms, it is to say that the Euler vector field is not tangent to x in this coordinate system, yeah? So we have Euler for f, but we take coordinates, maybe the coordinates are wrong, but it will follow that in some cases they are not wrong, yeah? So we cannot do anything better than that. And it is indeed so. So in that sense, the conjecture looks really, really difficult to hold without further assumptions of the singularity type. And below we can construct families of examples, but below I give you a certain example which is representative of these families. And it's exactly this pair. So I have a hypersurface with non-isolated singularity. So this is a classical example of a non-quasi-homogeneous hypersurface. And the singularity locus here is the x-axis, yeah? So we have this function f, which is equal to x. So you see it is a regular function, so it is non-singular, but still satisfies that its relative Miller and Turina numbers are equal to 1, so they're the same. But we see that in this coordinate system, they are not relatively quasi-homogeneous, so we cannot choose positive weights. The only possible weights is -1, 1, and 1, yeah? up to multiplicative constant, but it doesn't matter. You can throw this out. So to show that this is indeed a counterexample, we have to show that this pair is not relatively quasi-homogeneous in any coordinate system. And to show this, it is the same as showing that there does not exist a vector field lying in the intersection of these modules. So a vector field tangent to both x and y, which has positive rational weights, eigenvalues. And to show this, we just compute a system of generators of the intersection of these two logarithmic modules. And we observe, so I haven't written down the system of generators, but you can do it. So for example, you can use singular or other techniques and observe that for any vector field lying in this intersection, the 1z, so the linear part of this vector field is just some multiplicative constant times the Euler vector field, with minus eigenvalues. So we cannot produce any other vector fields with different eigenvalues, So it is one-dimensional, the space of 1z of this intersection. And the proof follows immediately since the eigenvalues are invariant, so they do not depend on coordinate systems. So what happens here? On the other hand, I would like to say, by the way, that if you take the intersection x equals 0 and x, so this x equals 0, f equals 0, and x with x, then you get an isolated complete intersection with this, which is quasi-homogeneous, But still, this shows that, okay, you can have an isolated complete intersection which is quasi-homogeneous, but you may not be able to extend the Euler vector field lying in the intersection, to extend it to an Euler vector field with positive eigenvalues in both hypersurfaces, So it is different. Why this does not hold? And the main reason that it does not hold, it is because the function f is regular function. So it can be made weighted homogeneous for any system of weight. So there is a lot of freedom there in order to include system of weights, systems of Euler vector fields with non-positive eigenvalues. And this freedom passes to the intersection, So if x is a non-quasi-homogeneous set, as in the example, then the pair cannot be made weighted homogeneous in any coordinate system. That is the point. But on the other hand, there are several important cases where such freedom does not exist. So there is more restricted. So you immediately have positive weights, and this is one of the results I will present here. That the relative sighting theorem holds true in the following cases: when f has multiplicity bigger or equal to 3, and x is any arbitrary analytic set, as long as, of course, the Bruce-Roberts-Milnor number is finite and we have equality of the Bruce-Roberts-Milnor and Turina numbers. And the other is when x is also a hypersurface, which has at most isolated singularities. Here at most, it doesn't really, I shouldn't write it, it can be smooth. But of course, there are other also cases. So I could write down C when x is a normal crossing divisor, and then conjecture is also true. But it doesn't really matter because we don't know other cases. So, for example, still we don't know. I will speak about this at the end if we have some time. If it holds when x is an ICs, most probably it holds. But I went ahead of myself. So how we do this, and I will try to make some sketches of the proof to see all the ingredients that lie there in this kind of difficult problem. Of course, this guy here, theorem 1a, is easy. We will use, in order to prove it, we will use some decomposition formulas of the Bruce-Roberts-Milnor and Turina numbers, which I will present now. So relatively trivial. So that whenever we start from Bruce-Roberts-Milnor number, and we say that whenever we have a pair with a finite Bruce-Roberts-Milnor number, then this is equal to the Milnor number of f plus some object here, a mu bar, which I will, let's say, call it the Bruce-Roberts number of the restriction of f on x, which is the dimension of this module. So it's the module of all vector fields, module of vector fields tangent to x, plus Hamiltonian vector fields of y. Y is the preimage of f, so it is the isolated hypersurface singularity defined by f. So it's all vector fields lying in the kernel of the differential of f, when evaluated on vector fields. And what is this object? So if you evaluate on df, you will see that this is just the Jacobian ideal of f modulo the relative Jacobian ideal of f. So this number is the codimension of the orbit of F under the diffeomorphism preserving X inside the orbit of F, yeah, under the whole group of diffeomorphisms. As you observe, as I already said, so this finiteness of this number comes immediately from this sort of exact sequence, yeah. So this guy here is the relative Milnor algebra. This is the Milnor algebra, and this is the kernel of the valuation map. And in the same way, we can do the same thing with the Turina number, which is the Turina number of F. The relative Turina number will be equal to the Turina number of F plus this restricted Turina number of the restriction, which is the dimension of this module. Here you see that there is symmetry. Yeah, I can change X with Y, whatever it is X, whatever it is X. So the dimension does not depend really on F. And then I compute the difference, yeah? So the proof is exactly the same. I take the projection and compute the kernel. And I take the difference and I call the difference Bruce-Roberts degree of non-quasi-homogeneity. And it's the difference of the Bruce-Roberts Milnor and Turina numbers. So by these two previous lemmata, or by directly, you can immediately show that the Bruce-Roberts degree of non-quasi-homogeneity is equal to the ordinary degree of non-quasi-homogeneity, so equal to the difference of the Milnor and Turina numbers of the function F, plus another positive constant, which is some type of degree of non-quasi-homogeneity, but not really, which is exactly the dimension of this module. So this module here is all logarithmic vector fields for Y. I recall that Y is the hypersurface defined by F, modulo all vector fields lying in the intersection, plus Hamiltonian vector fields for F. And these formulas we will need. We also have some further formulas. For example, when H is an isolated hypersurface singularity, but we will not need for the proof of the theorem. Up to now, we have all information, so it will be good to see some sketch of this proof. So we restate the proof of 1A as follows in terms of what possible weights can appear. Yeah. So if you have a pair with finite Bruce-Roberts number and the function f is of multiplicity bigger or equal to 3, then equality of the Bruce-Roberts Milnor and Turina numbers is equivalent to the relative quasi-homogeneity of the pair with respect to a system of weights, rational weights, lying in this interval here. So 0, open interval, 0 to 1 over 2. And this follows by simple calculations, because we recall that this equality of Bruce-Roberts Milnor and Turina number is equivalent to existence of a logarithmic vector field for X, such that leaves F as an eigenvalue, has F as an eigenfunction with eigenvalue 1. And it is equivalent by the previous corollary that the Milnor number, the ordinary Milnor number is equal to the ordinary Turina number, and to the equality of these restricted Milnor numbers. And the latter implies that any vector field, which is logarithmic for F, for Y, there exists a Hamiltonian vector field for Y, for F, such that their sum, or the difference if you want, lies in the intersection. So it is tangent, it's logarithmic for both X and Y. It lies in the, exactly, on this intersection. Now, since mu F equals tau F, the ordinary Milnor and Turina numbers are equal, and F has multiplicity bigger or equal to 3, by the ordinary Saito theorem, we know that there exists an Euler vector field for F with eigenvalues lying exactly in this interval. But by the second condition, so suppose that this vector field in these coordinates, it is not tangent to what? To X, yeah? Because if it is, there is nothing to prove. So immediately by second condition, we obtain that there exists a Hamiltonian vector field for F, such that the new vector field will be tangent to both X and Y. But we notice here that since the multiplicity of F is bigger or equal to 3, the 1z of any vector field which is Hamiltonian will be 0, yeah? Because they have non-linear terms, these Hamiltonian vector fields. So in the previous coordinates, the linear part of delta is immediately semi-simple, and so it has the same eigenvalues with our vector field. So applying Poincaré-Dulac theorem for this new vector field delta, we immediately obtain what we want. So applying Poincaré-Dulac theorem for this vector field means that we change coordinates so that x omega commutes with theta. Yeah, so it is of degree 0. And the change of coordinates is analytic because eigenvalues are positive, and that's it. Now, so we have proved what? That if the multiplicity of f is bigger or equal to 3, equality of the Bruce-Roberts, Miller, and Turina numbers implies the weighted homogeneous equivalent to the quasi-homogeneity of the pair, yeah? And this was kind of surprising. But still, this happens because you see that when y is an isolated hypersurface singularity of multiplicity bigger or equal to 3, then the space of one z is always one-dimensional. That's why it happens. So one could use also the Kersky-Alexandrov-Kersky theorem to solve this. But let me continue with the proof when the case x now, so f can be of any multiplicity, but the x has to be also an isolated hypersurface singularity at most. It can be smooth. But smooth I will not talk about. This is completely trivial and it follows at the end. I will show how it follows. So we state again the theorem, and surprisingly here, the theorem has been very difficult, actually, this part. So if we have a pair where with a finite Bruce-Roberts number and x is a hypersurface with at most isolated singularities, then equality of the Bruce-Roberts, Miller, and Turina numbers is equivalent to the relative quasi-homogeneity of the pair. With respect now to a system of weights lying in this half-open interval, so it's open from 0 to 1, yeah, and it's close to 1, so it can take the value 1 also. So it is unexpected, yeah. One would anyway, one would say so. Anyway, we'll see how it goes. So I split the proof in 3 cases with respect to the multiplicity of f. So if the multiplicity is bigger or equal to 3, we don't have to solve anything by previous theorem. So we consider the case when the multiplicity of f is equal to 2, so it has no vanishing to z. And this is the most difficult case. And let us suppose also that x also in case of multiplicity bigger or equal to 2, because if it is smaller, so it is smooth, it is trivial. So working again, we have what? We have first equality of Miller and Turina numbers of f. So by Serto's theorem, again, there exist coordinates in the Euler vector field for f, which has its weights in this half-open interval. So from 0 to 1 over 2. So this happens, this is what? This is a quasi-homogeneous splitting lemma of Saito, yeah? We have a function which is quadratic form, x1 squared plus x2 squared plus blah, 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 xk squared, plus some function which is multiplicity bigger or equal to 3, weighted homogeneous, so the weights up to 1 over 2. But let us suppose that this Euler vector field is not tangent to x in these coordinates. Because if it is tangent to x, there is nothing to prove, it is immediate. But you can make a lot of examples where it cannot be tangent to x. Again, by previous equality with this bar, yeah, there exists a Hamiltonian vector field for f, such that its sum with the Euler vector field will be tangent to both x and y. And let us denote now by W prime the eigenvalues of delta. So W prime, I say it is rational eigenvalues. We can always take it. Okay? In general, it is complex eigenvalues, but by lemma of Saito, we can see that we can take rational. So the eigenvalues of its linear part, and the linear part is just the Euler vector field plus the 1z of a Hamiltonian vector field. And here, 1z's are in general not 0, yeah? So there exist Hamiltonian vector fields with non-vanishing 1z. And so you can suppose that these eigenvalues, these new eigenvalues of delta, W prime, are different from the eigenvalues of the Euler vector field, yeah? Because if we say it is the same, again, there's nothing to prove. So let us argue as follows. Now, what it suffers to show? It suffers to show that we can choose these eigenvalues to be positive. And we argue by contradiction, and we claim the following. If there exists at least one weight, or one eigenvalue, one weight, which is non-positive, then the Bruce-Roberts Miller number of f with respect to x is infinity. So f is not finitely determined. And the proof of this claim, which I guess I have another 2-3 minutes to say about this, a couple of things, is using Sato's lemmata, some lemmata from Saito, because what? If we have k negative weights, then we can arrange all the weights to be symmetric with respect to 1/2. So we get k more weights which are bigger or equal to 1. And in fact, we can find coordinates x, y, z, which are weighted homogeneous. So these are negative weights. These are bigger than 1, symmetric with respect to the weights of x. And these belong to the 0,1 interval, yeah? So these weights. And in these coordinates, f is written in this normal form. So this is a splitting lemma. Here you see that the weights here are necessarily symmetric with respect to 1/2. And this is a function with an isolated singularity, which is weighted homogeneous with respect to the rest of the weights. So this we have. Now we choose some function which is a weighted homogeneous generator of the hypersurface x, yeah, and this we can always do. And suppose that the degree of this function is negative, then immediately we have that this function will have non-isolated singularities. So you can take this the degree to be positive, unless there is simply case which it does not change anything, the proof. So what happens is that we have that this function h belongs in this ideal y and z. So you see here y, the y variables, and the z variables, which are positive, yeah? So it cannot have negative variables because the degree is positive. So it can be written in that way. And we do what? We compute the singular locus. So h0 will have to be an isolated singularity. And computing the singular locus, we obtain that all these hi, the functions hi, will have their 1z evaluated on psi equals z equals 0 to be a linear formula in such a way such that the 2z of h is a non-degenerate quadratic form. So immediately we obtain that the degree of h is equal to 1. Yeah. So what we have done is we have reduced our pair f comma h to a weighted homogeneous pair with negative weights and necessarily the same degree d equals 1. And here you can immediately verify now by direct calculation that mu hf is equal to infinity. And this will give a contradiction. And this you can do it by direct calculation of the zero locus of the relative Jacobian ideal and conclude that this is a determinantal variety which defines a curve in C equals Z space in the C equals Z equals 0 space. Yeah. So it's dimension 1. So it is not an ISIS, so it is not finitely determined. So we obtain that necessarily there have to be all the weights W prime positive. Here you can immediately see, because forget about variable Z immediately. You have a pair of quadratic forms. And if you don't allow positive weights, so for example, 1/2, xi squared, yu squared, and so on, and you have only cross product terms, then it does not, this pair of quadratic forms does not define an isolated complete intersection singularity. Yeah. In order to this direct calculation, and you can see, and no matter how higher order terms you add, then nothing changes. So somehow what is missing is a quasi-homogeneous splitting lemma, yeah, which it is exactly that is the point. And finally, because I don't guess I have much time, okay, there is this trivial case where f is smooth, and I will not talk about it this immediate, it's trivial because h has isolated singularity. And just some final remarks, which are some open problems. So one is a conjecture. Is the relative Saito theorem true for pairs only under the simple assumption that the Miller number of f is strictly positive? So f belongs to m squared, which hopefully yes, but probably not. But we are not able to find any counterexample. The other is the relative Saito theorem true for pairs where x is an ISIS? And in the case, and the last one, in the case of ISIS, does the equality of Bruce-Roberts Miller and Urena numbers implies equality of the Miller and Turina number of the ICs defined by the intersection. So these are many other problems, but this is up to now what I had to say. Thank you very much. So if you have any questions.
Thank you very much, Konstantinos. I have. Can you show the last slide? Also,
yes.
please. I have several questions,
Yes.
but you put them in the last slide. But
Yes,
I want to do some comments, please. Can you present the last slide?
Yes. Can you see it now?
Yes.
Perfect.
In the question 3, maybe you can use some kind of Legruel theorem,
Yes.
because you are computing
Yes.
the intersection Milnor's numbers and Turina numbers, okay? I don't know if you tried to do it to solve this question, but I think that could be interesting. Another, please.
So yes, this is a great point, yeah, because if you prove too that the relative Saito theorem is true for ICs, then you don't have to prove 3 because it is brute force, yeah. Because pair will be weighted homogeneous, immediately the intersection will be weighted homogeneous. So the question is, can we find algebraically, with a priori, without knowing that it is true? Can we find this? And this is exactly what you say. It should be some types of Legruel formulas. But you know, Turina number is a difficult object for ICs.
Yes.
It has a simple formulation, but behind there is a lot of secrets going on. So it is not that immediate that you get it. Okay. Even for hypersurfaces, if X is a hypersurface.
Okay.
So
another comment, Konstantinos. It's the first time in my life that I see negative weights to compute weighted homogeneous situations.
Yes. Yes.
I don't know. You showed some slides before this.
Yes.
That you have some kind of general situation that any germ is weighted homogeneous if you can put negative weights. That's it.
Yes.
That's
yes.
it that you told
exactly.
me.
Exactly. So exactly, Marcelo. This is exactly what happens is that when UXF equals tau XF, you will always have in some appropriate coordinate system weighted homogeneity with negative weights. Yes. But in most cases, this will only be formal, yeah, in the formal category.
Okay.
Because that's the in an analytic, you can pass to the analytic category and say, okay, now I have a pair with negative weights, which is analytic, only if certain conditions of the eigenvalues hold, which are called, they're from the ordinary differential equations. They belong in the Siegel, in the Poincaré domain, and so on. So yes, you can have negative weights as well, yeah.
Okay. And another question that's quite natural, probably you have listened it all the time. What can you say about the non-weighted homogeneous case?
About the non-weighted homogeneous, that everything, this is amazing, yeah. Whenever you have non-weighted homogeneous, everything breaks down. It is amazing, for example, that you don't have Poincaré lemma, you don't have anything, everything breaks down. So for non-quasi-homogeneous case, you can't say almost nothing, yeah.
So I have a suggestion. I did it some time ago in another different point of view, but we considered the decomposition in the weighted homogeneous parts of the germ. Okay, fix a set of weights, do the decomposition, and then you have several weighted homogeneous with different degree parts of the germ. Okay, and the sum of the germ. If you restrict a little bit the change of coordinates that you compute to do the homeomorphism, you can do some. There are some change of coordinates which preserve the weighted homogeneous set that you fixed. That under this action of this weighted homogeneous, they are preserved. So you can do this change of coordinates in this sense, and maybe you can control, because the levels will become the weighted homogeneous and you change these coordinates. maybe you can do something else. I don't know, but it's a
I agree. Because you see, what we have is that in general, you have this, you have a function that has, or an analytic set, it doesn't matter, but it has an expansion to different degrees here with respect to a fixed system of weights. And then you try to find centers of coordinates that preserve the weighted homogeneity to throw away something, to throw away some tails or make the thing better. And this is also a thing that it is kind of non-trivial, because there is a problem with a weighted homogeneous part that might not have isolated singularities.
yes, I agree.
Has produced many examples like this, such that the principal part does not have isolated singularity, so you are lost. So something else also is needed. But it is also this, what you say, this is a direction also, yeah. So it's many problems.
Maybe. And just the last question, because we have time, and I'm not the only person that maybe can ask. I'm sorry. I lost. I will ask you later. Don't worry. Okay.
Okay.
Are there more questions in the public that's present? No?
Hello.
Hello, Maria. Hello, Cidinha.
I don't have question. I just want to say to Konstantinos that thank you, Konstantinos, for the very nice talk. And it was nice that you recalled that we started this work in Vitoria, right? So I'm really sorry that I cannot be in Vitoria this time. And in fact, 2 years later, and we are still trying to finish it. What very rich project. And in fact, another remark is that is a project with participation, Brazilian participation is very high, right? Because there are also very interesting results by Bombalesteiros and João Tomazella and Bruna Orefsi and Barbara. So in fact, it's being very nice to see how this subject progressed in the Brazilian singularity theory. Right?
That is true. That is true. Actually, it is very good that you reminded me somehow, because this I wanted to say that there is a very recent work by Bruna, Juanjo, Tomazella, and Barbara about they have computed explicitly formulas for the Bruce-Roberts-Milnor number defined on ICES. And I'm sure that, and also Carles has recently produced some formulas of this type, but they have to be compared somehow. And I think this is the first step in order to study better the difference, Milnor number minus Turina number for ICES, yeah?
Yeah.
It is the first step to go this road. So it is also a lot of work to be done.
This was going to be the question that I forgot before. Maybe not a question, but a suggestion. Maybe you can use Newton polyhedra to compute this difference between the Milnor and the Turina number. I know that to compute the Turina number using Newton polyhedra is not an easy task, but sometimes with very special situations, I know that is possible. And maybe you can do something in this sense, okay? That was the other question.
Yeah.
The good with this, Marcelo, is that when you are lucky when the function is weighted homogeneous, yeah, because then immediately it's just a plane. But concerning your previous question, when you have different degrees, expansion of different degrees, definitely this will be also a way to do things.
Yeah. Okay. Are more questions or comments? Yeah, please.
No, thank you. Thank you.
Okay. So if there are no more questions, let's thank you, the speaker, again. And I say hello to the people that is online. I didn't say before, sorry. Now we have the coffee break, okay? And we resume later. Oh, I have something to remember, please. People that didn't pay the registration fee, Please ask to Fernando to do it, okay, if you forgot, okay? Thank you very much.
Oi. Oi. Tá funcionando? Tá. Então tá bom.
Alô? Alô?
Alô? Ok. Não, eu só quero a lista. Obrigado. Alvaro Liendo. Podemos começar? It's my... Oops. Pode começar? Achou. It's my pleasure to introduce Professor Alvaro Liendo from University of Talca, Chile. Very beautiful place. And he is going to give a talk on singularities of T-varieties of complexity 1.
Hello. So thank you very much to everyone present here and in the video feed. So as just said, I'm going to talk about, I will try to, instead of pointing into the blackboard, just pointing here in my slides so that people in the video feed can also see what I'm doing. So I'm going to talk about singularities of T-varieties of complexity 1. And I'm not really someone from singularities. I'm more someone from T-varieties. So what I'm going to do is more telling you how T-varieties can be useful for singularities instead of showing you results about singularities themselves. Oh, important to say this is a joint work with, it's actually an old work with Hendrixius, which is named there, and a very recent work that went on the archive like last week, I think last week, with Antonio Laface and Joaquin Moraga. So Hendrixius, this guy here, he's from Manchester, and the other two guys, they are half Chileans. So this guy is Italian working in Chile, in Concepcion, and this guy is Chilean working in Princeton. So they are all kind of Chileans. Hendrixius is German working in Manchester. Okay. So the first question is, what's that? I hope you know. I've asked many people, what's that? Mathematicians could say whatever they want. If you are slightly from toric world, algebraic geometry world, or something like that, you're going to say that it's P2. If you're not going to say that this is P2, this talk is probably not for you, because that's toric representation of P2. Actual people say that's an angle, the angle of the room, or a flag. But if you don't see P2, I'm sorry, very likely, I will explain everything, but it's very likely that it will be too fast for you to follow. So I hope you all see P2 there. And the picture you have there, it's called a fan. And the name, the plane where this picture is located needs to receive a name, and it's usually called NR or NQ. I use Q instead of R. It makes no difference, and I'm not going to explain deeply enough for the difference of that to make sense. But I do want to explain a little bit. So that picture is composed of 3 smaller pictures. These smaller pictures, they look like cones. So these are cones. And each one of these cones represents an affine variety. So in this case, each one of these cones represents A2. So we have a copy of A2 here, a copy of A2 here, and a copy of A2 here. So the red, blue, and green cones. And the way, of course, you can always glue 3 copies of A2, but you can get many things. It's not for sure you're getting P2, no? You can also get weighted projective spaces. And you can get many other things if you glue them widely. You can get non-separated varieties and stuff. But the way these cones are located in the picture, so in the plane where they are drawn, kind of says the way they have to be glued. And the way they have to be glued, these particular cones, the way they are set up, you come out with P2. So this is toric geometry in 1 minute. The 600 pages book by Cox and company on toric geometry in 1 slide. So this part we've already seen it in a talk I have wait. If you're not seeing me, I have the name written here. So Thais Maria Dalbello, he did the exact same thing in her talk. She really explained this with much more detail than what I'm going to do. So I just want to show you, so this is of course one of the cones. Yeah, I took the green one. I could have taken any other one, but I took the green one. And I want to explain to you how I get an affine variety from the picture. So to actually make the picture more serious, I have to give some details. So as I said before, this is living in some space that is called NQ or NR. I'm going to be using Q all the time, which means vector space. Yep. And it's 2-dimensional in our case. And as a 2-dimensional vector space over Q, it has a dual. And the dual, I'm going to be calling it MQ. So I actually erased part of the Q. So I'm going to be calling it MQ. And the cones receive names. So in this case, they are called sigma. It was written before. And I can take the dual. I never gave generators for these cones, but this cone looks like it's generated by 0, 1. And this one, the picture is not so, yeah, it's a little bit crooked here, because my screen is wider than the projector screen. So for me, it really looks like this is 1, 1. Wait. For me, it really looks, it doesn't look here for those who are present, but in my screen, it does look like this, it's almost 1, 1. So if you take the dual, when you take dual, on the dual side, I also drew the integer points, so it's easier for us to see, and because the integer points are going to be important. I drew the integer points, and the dual of that cone, it's very easy. I hope the picture looks reasonable. You just take the inner normals, so the inner normals seen on my screen is like that. Yeah, it looks good. So it's evenly crooked. So, and the inner normal, here it looks like that. So these 2 directions are actually the directions forming the other cone. And to get an affine variety from the picture, you need to get yourself a finitely generated K-graded algebra, where K is going to be the field all the time. So the way to get a variety or an algebra from that is just take a look at the integer points. So the integer points inside the dual cone are kind of these, plus the two red ones and the 0 one. Yeah, the red ones, I have them signed for a reason. And now you can build this set of points, the orange ones, plus the red ones that were marked before. They form a semigroup, and you can create the semigroup algebra for this semigroup. So this is the semigroup, exactly this, the dual cone intersected with integer points that I call them M. I'm actually giving all the definitions from toric geometry that I will be needing in the sequel. So you could say I didn't really need to name them N, that's Z2, no? That's the integer to the power 2, but the names are going to be useful later on. And then I just make sums. I make direct sum, one character, one new symbol, which is this chi I have here, for every element in the semigroup, and I put a copy of the base field in every place of this semigroup algebra. I still need to give you, okay, this is a vector space, so you have the sum. I still need to give you the way to multiply them, and the way to multiply them is exactly what you expect. They are called chi, because chi m times chi m prime is going to be chi m plus m prime. So vectors in these cones, they can be summed. You can add them up. And then, not to make stupid things, I have to get 1 when I take the 0 vector inside that semigroup. And in this particular case, you can easily see that this is, in fact, the affine space. So to be the affine space, the algebra has to be polynomial algebra in 2 variables. That means that it needs to have only 2 generators. It's very easy to realize that generators of the semigroup algebra corresponds to generators of the semigroup. And now, I'm sorry, I'm going to come to the screen. And it's very easy to see here that these points, the red ones, actually generate. You can take, I don't know, if you want to create this one is obtained by making this one plus this. If you want this, you need to have this, and so on. So sorry if you are on the video feed, I couldn't resist. I tried to resist going to the screen, but it's my first time after the pandemics. So it's the first time I can actually go and point out in the board. So the red ones actually seem to generate, and they are generators. They satisfy no relationship, because there is no way to build some sum that gives 0 with those. So they are free generators, and actually you realize that your algebra is the polynomial algebra in 2 variables, chi to the power -1, 0, and chi to the power -1, 1. They're here. Let me use different color, this one and this one. So the picture was actually showing you the affine space. We had 3 pictures. If we do the same thing for the 3 pictures, you will get 3 times the affine space. And as I said before, the way they are glued together is given by the relative positions they occupy in the space, in the plane. I will not describe it because this is a singularity conference, and very often in singularities, you don't really need the full variety. Everything is local, so you just take the affine piece. And it's great because the affine part is much easier. If you know toric geometry, I will be taking 10 more minutes to explain the way these are glued. So I will not be doing it. Now, I'm not talking about toric geometry. I promise T-varieties. And T-varieties are exactly toric varieties, but where the torus that act is smaller. I will also be giving a definition later on, but I want to show only pictures at the beginning. So if the picture I showed before says projective space to you, this picture doesn't look so weird. It has many common features with the previous pictures. So there is something that looks like a fan, like the previous definition that I have one of them here. And there are 2 others that look like fans, but up to some compact part, they are not really fancy. They don't look that much as a fan as before. Actually, this is going to be called a divisorial fan, and this is object that I have written right here. So we have a variety, and I mark some points. So the base variety is called Y, and I put P1 for my example. And I marked 3 points. Those 3 points were 0, 1, and infinity, very common points for P1. And then I drew some strange pictures on top of them. Yes, these pictures with red, green, yellow, and blue. And as I said before, I would like to call this a divisorial fan. And this is going to be the object classifying T-varieties of complexity 1 that I will define in a moment, which is a slight generalization of toric varieties. I forgot to do something, wait. There. So let me, as I said, I probably said it already, but this is a three-dimensional variety with a two-dimensional torus action. This is what is encoding these pictures. I will show you a little bit about it. So it's separated and complete. The same way as the previous, if you know some toric geometry, in the previous picture, the fact that it's complete comes from the fact that the pictures cover the whole plane. Here, the fact that the pictures cover the whole plane says that the variety you obtained is separated, it's complete. And the fact that the cones in the previous pictures do not overlap, so red was not overlapping blue. The fact that they do not overlap says that the variety you will obtain is separated. Here the same thing happens, so it's separated and complete. And this particular picture corresponds to a very well-known variety. It's the smooth quadric in P4, which happens to have, it's three-dimensional, it has a two-dimensional torus action, but no more. It cannot accept a three-dimensional torus action. Good. So after these 10 minutes of all toric geometry in a few slides, just some notations that are typical for toric geometry. I hope you have seen them before. As I said, it's going to be, I hope you've seen some toric geometry before. So just standard definition, so the base field is going to be called K. It kind of needs to be algebraically closed, but no more than that. I'm characteristic 0 guy, so don't ask questions about characteristic P. But some people have done, I have also done some things there, but I'm mostly characteristic 0. I'm afraid of other characteristics. So GM is going to be the multiplicative group of the base field, so that the torus is just the multiplicative group to the power n, which I will be denoting by 10 or t by t or t sub n. So the m that appeared before is the character lattice of Tn, and it's nothing, no, it's not equal, but isomorphic. This is isomorphic to z to the power n. So I have to make a vector space with that. So the vector space, I create vector space by tensoring with Q. I could have done it with R. If you've seen toric geometry, some people do it with Q, some others do it with R. And then n is the dual. So this is nothing but the dual of m. And so nq is the dual of mq. And I've already done it. I've denoted cones by sigma. And all cones will live in n. And all the duals are going to be living in the dual. And then I have fans, but I'm not using fans today because it's singularities, and so everything would be affine. And then the usual standard categorical notation. If you get a cone, I kind of explained you how to get a variety from it. I will just be denoting it x of sigma, the variety I get out from that. And now some definitions. So I took 17 minutes without actually saying anything about math. So a T-variety, the thing I'm talking about, is a normal variety with a faithful torus action. Okay, it's true. So a T-variety is a normal variety endowed with a faithful torus action. The complexity that I have used many times and that appears in the title is the codimension of the generic orbit. Actually, this definition is not explicit to torus actions. So if whenever you have an algebraic group, a linear algebraic group acting, you call the complexity of the action, the codimension of the action of a generic orbit of the Borel subgroup. Since the torus, everything is the torus, so the Borel subgroup is the torus, it's just the codimension of the generic orbit. And since I call for the action to be faithful, this I can do because tori, they have a very well property that if I quotient a torus by any subgroup, I get another torus. So I can always assume that I started with a faithful action. If I have a kernel, I just mod it out and I will get a different torus. So since I called for it to be faithful, I can just say that the complexity of the variety is nothing but the dimension of x minus the dimension of the torus acting. Very simple. but the original definition was that one. So the best known example, as I said before, of T-varieties are toric varieties, which correspond to complexity 0. So if you, again, if you've ever seen a toric variety, that's the definition. So a toric variety is an algebraic variety endowed with a torus action having an open orbit, open dense, because it's Zariski open. So open dense means that X has the same dimension as T. So it reads as the complexity being 0. And toric varieties, they have a very nice combinatorial descriptions by fans, which I kind of showed before. And the main point is that it's not just drawing pictures and obtaining things. It's actually a categorical correspondence. Many geometrical properties from toric varieties can be read from these pictures in combinatorial ways. So they are kind of appealing, because if you have kind of any theory, you can go and test it, because you can actually compute things. Have you ever tried to compute anything in algebraic geometry? So it's impossible. Unless you're dealing with curves, sometimes surfaces, and later on it's impossible to compute anything. Okay, toric varieties are a tool where you can actually go and compute stuff. So they're very useful as examples. And then somewhere in 2003, I was not even in mathematics yet, but I was about to go into mathematics. So two people, the first guys is Altman and Hausen, old guys, not that old, but at that time they were old for me. They kind of generalized this theory of toric varieties to higher complexity. Of course, you have to pay a price. It's much more complicated. But there is some idea to encode all the things that can be encoded combinatorially, to encode it in combinatorial terms. And later on, Suze and Ilten, which are exactly my age, so we were all on PhD at the same time. They were in Berlin, I was in France. They further up this theory, and they did the gluing process, so to get from affine to global varieties, and they started doing many things. And then I jumped along the train at some point around there. Good. So as I said before, this is the picture for some particular T variety. And again, you have the feature that colors separate this picture kind of in 4. I'm not going there, I'm doing it here. Kind of in 4 different pieces, these 4. And you may expect, if you believed what I said before, you may expect that this actually corresponds to the affine pieces. And it's true. And the relative position they're sitting in the plane, or in this variety times plane, they will be giving you the way you have to glue them to get a global variety. But again, since this is singularities, we only keep the affine part. As before, the first thing was a picture, and actually the picture was not looking that good in the screen, because the screen is a little bit crooked with respect to the size of my screen. So I need to give some numbers to make this mathematics. So I'm saying that these pictures correspond to this is 0, 0. So these are the vertices of this picture in the plane. All of this is, sorry. All this is living in NQ, which is nothing but the vector space of dimension 2 over the rational numbers. Maybe I will erase this. This picture does not have it, but the slopes of all the lines you see here are either 0, 1, or -1. So they are really, I don't know, 45 degrees. They look like that in the picture. Good. And I would like to spend now maybe 10 minutes to try to show you how I get a variety with a torus action from this picture. So the first thing we're going to need is a definition. This definition is the definition of Minkowski sum. So Minkowski sum, you may have seen it before. If you've done some toric geometry, you have seen it before. But it's very simple. The Minkowski sum of two sets is just all the possible sums you can write between elements of one set and the other set. So in this case, if I want to add this segment, the segment 0, 0 to 1, 0, with this cone, the cone that starts in 0, 0, and the two rays that create the cone have slopes 1 and -1, what do? Okay, I have to sum up all all the points. But since all my pictures are convex, you may remember from geometry at school even, that if you're going to add convex stuff, you only need to add the vertices. So if I add this vertex with this one, I get this one. If I add this one with, or maybe different color, if I add this one with this one, I get this one, and then you get the same shape as before. So it always happens when you're adding up convex objects. So this is the Minkowski sum of the two sets on the left. I'm actually using the same picture again. It's the same picture but twisted. I would like to define what a tailed polyhedra is. So as in everything on toric, I'm taking one particular cone that I call sigma, and then I can add any other polytope that is compact. Okay, polytope. I think polytope for me means bounded. And I don't say compact because I'm using the rationals, not the real numbers. So if I were using real numbers, it would be compact, but it looks compact in the picture, but it's not. But bounded it is. So a polygon, a polyhedra, that's better. A polyhedron with tail cone sigma is exactly any polyhedron that can be written as the sum, Minkowski sum, of the cone sigma and something that is bounded. Of course, this bounded thing that I have to add is not unique at all, so you will immediately realize that if I add that polytope instead of the one I had before, I get the same thing, because I'm going to be adding this vertex, I'm going to be getting this one, but also this one and this one. You don't see them. This one and this one. There. But then you lose those two vertices when you add up the cone. So it's not unique at all, but it's still something compact times the cone. So this is a tailed cone. And then I will just some names that I will be using, but it's not too interesting. So I will denote by this all the possible polyhedra that I can draw in NQ with one fixed tail cone sigma. They are called sigma polyhedra. And this is a little bit more interesting. This set that I just defined, I can add them up, because if I have one, so the sum, the Minkowski sum of a cone with the same cone is the same. So if I add some compact thing plus cone plus compact plus cone, the two cones, they add up, you get the cone, and you get compact plus cone. So it's again something compact plus a cone. So they do form a semigroup under Minkowski addition. And this semigroup is even a monoid, so it has neutral element. The neutral element is just the cone sigma. Because if I take a sigma polyhedron and I add the cone, I'm doing nothing at all. Good. So another thing that you've seen before, if you've seen toric geometry, you used to define you use it to define many things, but in particular, it's used when you define ample divisors. So if you have, I don't read it, it's much easier to explain it. So the definition of support function is this. If you've seen it before, that's it. If you've never seen it, don't look at it. I'm just explaining it in the picture. So I have here my sigma polyhedra. So the domain of the support function is the dual cone of my sigma polyhedra, so sigma dual. Now, my support function is going to be piecewise linear, and is going to be given exactly by duality with vertices. So I will be taking duality with one vertex or the other. And the one that I take is the one that gives the minimum possible. So again, to realize where the vertices change, as always, when in doubt, you just take inner normal. So the inner normal here is the one that's giving you exactly where the chosen vertex is going to change. And on this side, the chosen vertex is this one, and on this side, the chosen vertex is that one. And any point here is going to be denoted as M1, M2. So duality of M1, M2 with 0, it gives 0, of course. And duality of M1, M2 with 1, 0 gives M1. So this is the support function. Nothing particularly complicated. And now I go to the complicated object. So to begin with, to actually obtain affine stuff at the end, I need to start with a variety, but not just any variety. I want a semi-projective variety. So semi-projective variety, it looks like a huge name, but it's not that much. It's just something, whenever you have a variety, you have a morphism to the spectrum of global functions. You ask for that morphism to be projective. So the definition of beings, there is also semi-affine of definition, which asks for that morphism to be proper. So in this case, we ask a little bit more, we ask for that morphism to be projective. If you don't know, then the concept is not that important, but affine varieties are semi-projective, projective varieties are semi-projective, and blow-ups of semi-projective varieties are semi-projective. So all those three examples are the most important. What is not semi-projective is like the affine plane minus a point, because it's not proper over its set of, so it's not proper over the spectrum of the global functions. Good. So now I want to define the main object of today, which is here. So a polyhedral divisor is just the same way you define divisors the first time. So the first time you see divisors, you just define them as a formal sum of codimension 1 varieties in your variety, and the formal sum, you take the coefficients to be in the integers. Yes, that's the definition of a divisor. But then, if you kept on algebraic geometry on the classification line, then you say, okay, integers is not that good. I have to take rational coefficients, because if I want to run the Mori program, I will need to be using rational at some point. And then they say, actually, rationals are not that good. I have to take real to make things work. And actually, we have to take something much stranger, which are exactly these tailed polyhedra. So the main object classifying T-varieties is going to be a polyhedral divisor, which is a divisor on a variety, but where the coefficients are not integers, are not rationals, but are polyhedra, like in my picture at the beginning. So I hope the picture makes a little bit more sense. So now let me explain you quickly in which way I'm going to get the algebra. So of course, I'm not going to prove anything, but I'm going to explain how I get an algebra from these pictures. So, do you remember that the object I defined, maybe it's not the best of colors. So the object I defined was that. Okay, that's, forget the notation, but it's exactly a divisor whose coefficients are polyhedra, sigma polyhedra to be exactly. So what I can do is take the same divisor, but instead of taking the polyhedra, instead of taking the polyhedra I put as coefficients, I change them by the support function. So this is the support function. And now, do you remember my explanation of the support function? I can evaluate the support function in any element in the dual cone. So there is a dual missing here. This is great, I can correct my mistakes here. So this is sigma dual. So I take any element in the dual, and I can evaluate in this particular M, but by just putting M inside the support function. And now this is an honest Q divisor. I don't need to convince you that it's a Q divisor, because everything is over Q. So I only get Q as a result. If I had chosen R I would be needing to explain, okay, the vertices were rational, so I'm getting something rational. That's the reason I use the rational numbers. And so, this way, I can get for every m, this is the important part, for every m in the dual cone, I can build myself an honest Q divisor, actual divisors, not with z coefficients, not with integer coefficients, but divisors with coefficients in the rational, which is what it says here. And the only actual property I'm going to be needing from all this I did, if you remember, I took the support function of something that was convex, yes? And so the support function of something that is convex is concave. So the support functions are concave, and then I made some sums. So this application I just created two divisors is concave in this sense exactly here. So when I take the evaluation of my divisor in one m and the evaluation of my divisor in a different m, so there's a prime missing there, I have to get something, it's again a Q divisor, but it has to be smaller or equal as divisor than the evaluation I obtained at the sum. And maybe I skip that. So this is, in this part, I could have shown you exactly how do we get the divisors from my example, but it's a little bit technical, and I have already spoken too much without saying anything about singularities. So the way you get an algebra from this picture is the following. So again, we start as before with a P divisor, with a polyhedral divisor. And then I'm going to build an algebra in a very similar way, the way I do it for toric. So do you remember for toric? I take the sum over the integer points inside the dual cone, which was my semigroup as before, and then I put these characters that I defined before. I put this symbol here, and in toric, I was just putting here the base field. So in this case, I don't have to put the base fields, but I have to put something related with the divisor I built. So what I have to put is global sections of the evaluation divisor. And of course, once I have an algebra, I just take spec and I get an affine scheme. Oh, I lost what I've written before. I just can show you that, or maybe not, but simply the multiplication rule, of course, is going to be given as before. So the multiplication rule is I multiply characters the way they are intended, and functions, they are multiplied. Just if I have a section, if I have a section in divisor in evaluation M and a section in evaluation G, I just multiply them to get a section in evaluation M plus M prime. And here I just prove you that actually F times G is a section in the sum. And that's where I'm using the concavity. Because if I have that F is a section on one side and G is a section on the other, on M prime, okay, when I multiply them, I will be getting this. This is just trivial. But by concavity, I get this second part. And this tells you that FG is a section in the divisor M plus M prime. So evaluation M plus M prime. So all this, up to this kind of shows, without much detail, but most of the proof is there, that A of D is indeed a K algebra. Okay, but to be an affine variety, I get an affine scheme. But to get an actual variety, I need to impose some conditions. I need that A is finitely generated at least. So I'm not explaining this at all, but the actual conditions I have to put on a polyhedral divisor to make the algebra of an affine variety, so to make it finitely generated and having the right dimension, are exactly these. So do you remember that D was a divisor on a variety Y? So the variety Y is just a semi-projective variety, and I have to ask some conditions for the evaluations. So the evaluation divisor for all M, wherever it makes sense, which is the dual cone, has to be Q Cartier, which means that a multiple of it has to be Cartier, and semi-ample, that I'm not explaining what it is. And the evaluations, not everywhere, but in the interior of the cone, have to be big, which again, I'm not explaining what does it mean for a divisor to be big. But these are perfectly well definitions in algebraic geometry. The important part, that if I restrain myself to complexity 1, everything is much, much, much easier. So I'm going to restrain myself to, so in the sequel, to not only complexity 1, but the most interesting part in complexity 1, where the base variety is P1. So it's where all the interesting geometry happens. So if, on singularity terms, when the base is not P1, the singularities are awful. And when the base is affine but not P1, you get toric stuff. So the only part where you get new and reasonable to handle stuff is P1. So in that particular case, the actual conditions I have to put to obtain an actual affine variety, not just an affine scheme, is very simple, is that the degree of the polynomial has to be a subset of the cone. So do you remember what degree was, no? So the divisor in question was like a formal sum, like that. And when you take the degree of a divisor, you just sum the coefficients. So here it's the same. You just take sum, and then the sum has to be Minkowski sum. These are all sigma polyhedra, so these are all polyhedra with tail cone sigma. This could be contained or not in sigma, so the condition is that it has to be contained, but it cannot be exactly equal to sigma. So it's very simple combinatorial condition. So again, my example as before, which I already kept the way I showed to compute the evaluations. And now the theorem. So I've been telling you all this stuff because there is a theorem, and these are the two guys that were old at the time, but they probably were as old as I am now at the time. So Altmanhausen proved in 2003, I think I said, but it was published much later in 2006, that if you take a p-divisor on a semi-projective normal variety, Y, then the process I did before, so from these p-divisors, you build an algebra, and you take this algebra, you take spectrum, and you get a variety, okay, is indeed a normal affine T-variety of complexity, the dimension of the base variety. So if the base variety is P1, you get a T-variety of complexity 1. And of course, it's not just constructive, it's actually the hard part of their theorem, is to prove that you get them all. The converse is, if or whenever you have a T-variety, then this T-variety is equivalently means isomorphic with isomorphism that respects the torus action. So it's an equivalently isomorphic to x of d for some p-divisors on some semi-projective variety. Y. So this is the classifying theorem. It looks a lot like the classifying theorem for affine toric varieties. Well, good. Again, I said the particular example, if I had shown you all the details in the example before, actually the particular example was the affine space. Just the three-dimensional affine space, but with a two-dimensional torus action, and that's the action. And again, the gluing process, I will not be talking about it, but I just have to say this so that you don't believe that this world is magic. So all these pictures only work in complexity 1, which is the case I'm interested in. So for me, it's good, but not in the general complexity or in the generality that I gave the previous theorem. Good. So maybe just take a couple minutes to tell you what's been done. I will not be naming the guys. The names are there. So the combinatorial description itself, as I said, was these guys here. The nice pictures I showed you, I did the pictures, but the theory that supports the pictures, it was by Iltensius. These are all the guys in the first line. And then they, and I jumped along at some point, we just took the book on toric geometry and start trying to do the same things they did before. So the part on divisors on Picard group was already done before me. And then Cox rings, which of course are very easy, are very interesting and object to handle. T-varieties of complexity 1 that have the base P1 that are rational, are Mori dream spaces. So they have finitely generated Cox rings, so you can do all the Cox stuff to them. So again, a toric variety you can characterize projective toric varieties by in terms of certain polyhedra. No? So that part was also done by Ilten and Sus. Study of the formations of toric varieties is also interesting, and you can do it. Again, the process of finding generators of a semigroup algebra is called finding a Hilbert basis of the semigroup, which is what I did in the first example. No, the red points are the generating ones. There are algorithms to do that, and this was also done in our case. Then this is my stuff. My main stuff is study other groups acting on varieties that already have a group acting, in particularly additive group actions on varieties who already have a torus action is my stuff, so I work on that. And Kevin Langlois as well, he's my mathematical brother. Then again, the same thing, SL2 actions on T varieties is again me, with Archancev, someone from Russia. And then if you're already having stuff acting, you may have all of them that act. So if you are projective and maybe complexity 1, you are Mori dream space, your automorphism group is linear algebraic, you can compute it. So we worked at some point in computing that. Then once a theory is created, of course, people jump into it to see what else can be done. So some people have tried to change the group by a different group. It works up to some limit. Vector bundles have been studied. Again, I'm just telling stuff that's been done, so if you're interested, you can take the names or you can ask me. So Kähler-Einstein metrics have also been studied by some of these guys. For characteristic people, they did some, they described, this is also complexity 1, the Frobenius splitting. Some topology, so here someone is missing. Langlois has also worked on the topology. Then Okunkov bodies, this is kind of escaping what I do. Again, uniform rationality conjecture has been studied in this context. Cox rings of projectivization of toric bundles. Toric bundles are not necessarily toric, but they carry the action of the original torus. So you can study them. This is flexibility, an affine concept from that my former PhD advisor studies. So I put it here. Characterization of smoothness. And then we're going into the singularity stuff. I put it here. So in an old paper by me and Hendrixius, we gave a way to find a partial resolution of singularities in terms of these combinatorics, kind of following the way you do in toric. And we study rational singularities and some other things. So very recently, with myself and Sus, no, this is also the old paper. We studied canonical terminal, log terminal singularities. So the singularities appearing in the minimal model program. And this is very recent. So we studied Dubois singularities. We characterized them. And much more recent than that. So in March, these guys, so this is, I said, this is my mathematical brother. This guy, I know him because he visits someone at my institute very often. I tried to read the introduction just to say something, but they settled Nash problem for varieties of complexity 1, the same way it has been settled for toric. So this is also quite recent. I have no idea of that, but I give you the names of the people. Good. So I'm still having 13 minutes to talk about singularities. So let me give you just a short and slight idea of how you get a, not, okay, I'm a little bit optimist here. It's not really a resolution, but it's a weak resolution that we're going to find. Weak means that I get something that is smooth, but I may change the smooth part of the original variety. But sometimes just weak resolution is enough to compute many things. In particular, to all the things I said before, it's enough. So now I need a piece of machinery from algebraic geometry. So do you remember I said that the definition of the algebra was like this? So taking global sections of each evaluation divisor and put them together in a direct sum. But I could do, instead of taking global sections to begin with, I could just make the direct sum of the sheaves. So now I'm getting this is not a standard algebra, but it's an O of Y algebra. So it's a sheaf algebra. And of course, if I take global sections now, I'm going to recover the algebra I started with. But I don't have to take global sections now. Here, sorry. I don't have to take global sections now, because I could just keep my original O of Y algebra and take relative spectrum over the base, over Y. So this is standard from algebraic geometry. I take an O of Y algebra. I cannot take direct spectrum, but I can take relative spectrum over the base. And for free, with all these constructions, you get yourself, so this one here was a relative spectrum, so it has a morphism to Y. This one here, I can get this morphism up here from the global sections functors. I'm taking global sections to get the other one, so that also gives you a morphism. So I get a picture like this. And you can prove in all this picture, I will erase my lines, that this R here is proper and birational. And this one here is good quotient. I think I won't be needing the good quotient part. But this, the important part is that this here is proper and birational. So it kind of looks like the beginning of a resolution of singularities. If the singularities in X tilde are nice enough, I can use this as partial resolution of singularities if I can keep resolving these singularities. And that's exactly what happens. But to actually explain you how we do it, I need to tell something that I haven't told before. So how unique is all this description? It's not that unique. So of course, you can always do automorphisms of the torus. And this reflects in base change in N. This happens already in toric. So if you've seen toric, so the three pictures I had in my first slide, they are all the affine space. They are different pictures, but they are all the affine space, because there is some automorphism of the torus, taking one into the other. Then there is also the choice of a rational equivariant map from X to T. I don't want to talk about it. This is just to be completely honest. Automorphism of the base, again, I can always, the same way I can take automorphism in the torus, I can take automorphism in the base, but this is the one I'm interested in. I can also make birational modifications of the base. So, this is some mistake. If I take my original combinatorial description in a Y and I take any projective birational map from Y prime to Y, I can pull back my divisor and then I obtain a new representation of the original T-varieties, but I am changing this tilde version. The relative one changes, but the absolute one keeps the same. So, using this in a very condensed, resumed way, we can actually define that we're going to define the P divisor to be SNC, like simple normal crossing, if the support is simple normal crossing plus Y being smooth. And you can prove in that particular case, so if your base variety is smooth and the support of the divisor are simple normal crossing, then this X tilde is toroidal. So being toroidal means that you're locally toric. It doesn't need to be globally toric, but in every point, there is a étal neighborhood that is isomorphic to an étal neighborhood in a point in a toric variety. So it's locally toric. And then this means that if you have a divisor that is SNC, you can use that morphism that we had before as a weak partial resolution of singularities. And in particular, X tilde has only toric singularities, so all singularities are at most toric. And again, this is great in complexity 1, because in complexity 1, you don't need to take care of anything, because all P divisor are SNC. So in complexity 1, if the base is P1, you have everything you need to obtain a weak partial resolution of singularities, which is exactly what we did in that paper with Hendrixius. And then when you have it, you can use it. So if you have a weak partial resolution up to something that is nice for that concept, you can use it to characterize it below. So in particular, toric singularities are all rational singularities. So you can use that weak resolution to characterize rational singularities below. So Here's the definition of what rational singularities means. Maybe, yes, I will explain it. So if you have a variety and you just take any resolution of its singularities, there is always a map from going from the structure sheaf of X to these higher direct images of the structure sheaf of the push forward of the structure sheaf of W. So varieties called to have rational singularities if actually these push forwards are these higher direct image sheaves are trivial for all I greater or equal than 1. Actually, for 0, they have to be O of X, that's equivalent to being normal. Since all my varieties are normal, I don't need to put that condition. So if you knew what rational singularities is before this talk, there's also a condition for for I equals 0, but that's equivalent to being normal. So since I put normal in all my varieties, get there. And then there is a more cohomological definition, but I will skip it. So I now restrain completely to complexity 1. So all these statements, or not all, but many of these statements, we made them in general complexity, and they are hugely complicated. But in complexity 1, they all become strictly combinatorial. So this is the first result I want to show you in this last 5 minutes. So if you have a p divisor, so the object I've defined through all this talk, then this particular X has rational singularities if and only if you just take the evaluation divisors, you remember they are Q divisors, so you round them down to get a Z divisor, and this Z divisor you compute degree. So degree is an integer number. The condition said that for the original divisor with Q coefficients, it has to be greater or equal than 0. But in the round down process, it could go below. So if all the evaluation divisors have degree, round downs of evaluation divisors, have degree greater or equal than 1, you have rational singularities. If not, you don't have them. So since all toric varieties have rational singularities, let me give you an example of a variety that does not have rational singularities. So we take, so this is a mistake, this is just the torus of dimension 1, and then we take, and the cone I'm going to be choosing is just so in dimension 1 means that n is just like a straight line like this, no? And there are not too many cones. So the cone I'm taking is that half size, that half line. So the divisor itself is going to be the sum of 3 points, 3 marked points with 3 coefficients, and the 3 coefficients are, so the 1 and 2 is 1/4, minus 1/4, and the third one is 3/4 plus sigma, of course. And these numbers are chosen so that when you take the evaluation divisors, so the evaluation divisors for 2, 3, 4, 5, and so on, they all have degree greater or equal than -1. But the evaluation divisor exactly in 1, okay, let's evaluate in 1. Believe me that this is what the evaluation, it's duality with the only vertex you have. So it has to be this. And you get -1/4, -1/4, and 3/4. So when you round down, the 3/4 disappear, and the -1/4 and the -1/4 became -1. So you get -Z1 minus Z2. So the degree of this round down is -2. So you predict that the singularities are not rational. And indeed, in this particular case, since you can compute generators and all those, you can actually get the equation. And the equation is that one. And this is a very well-known surface that does not have rational singularities. So it actually has elliptic singularities, which we can also prove with our theorem. But I did not explain that part. So in one example, the theorem works, and it's, as I showed you here, completely combinatorial. Nothing to do, nothing to actually go and compute cohomologies as you should have. So a second example that it's again doesn't have toric, or maybe I'll skip it. Good. So another result on the same line is Cohen-Macaulayness. So again, definition, a local ring is Cohen-Macaulay if its scroll dimension is equal to its depth. Just words if you don't know what Cohen-Macaulay was before, because I have 2 minutes. And a variety is Cohen-Macaulay if it's Cohen-Macaulay in every point. So all local rings are Cohen-Macaulay. And again, something we can prove, it's not full criterion, but it's full for isolated singularities. So if you have a P divisor on P1, and you assume that your object has isolated singularities, so at the vertex you only have one, and everything else is smooth around, assuming that the dimension of the torus is 2 or more, then Cohen-Macaulay is the same as having rational singularities, so you don't get anything new. We don't need to handle the case t equal 1, dimension of t equal 1, because in that case you have surfaces, and the surface is normal. Everything has been normal for me all along. And normal surfaces, they are all Cohen-Macaulay, so there is nothing to be done in that particular case. So it's a full criterion for Cohen-Macaulayness in the case of isolated singularities. And the final, you always have to talk about something recent. So everything else was from at least 10 years ago. This is from last week. So again, Dubois singularities are some kind of singularities that are interesting for the people in minimal model program. And they have some really complicated definition. So if you have a normal variety, you have to, so this T is not the torus, sorry. So you take X and you embed it in a variety, which I call T, which was stupid. Let's call it, I don't have more numbers. Okay, let's keep it T. And then you take a log resolution of this variety, the variety where you embed it. And then you just take the exceptional divisor of this, and then you have to give the same condition as for rational singularities, but for the for the exceptional divisor of this embedding. It's a complicated, very, very technical definition that I don't understand. So one of the co-authors of the paper works in minimal model program. He was interested in that. But then the important point is this. It's a very complicated definition, a very complicated notion of singularities, and people in minimal model program, they don't have examples, because it's impossible. With all these definitions, it's impossible to actually build examples. But for us, in the case of complexity 1, assuming that X is Cohen-Macaulay, we need for some technical reasons to assume that, this Dubois condition, which is hugely complicated, becomes this, which I'm actually not going to explain because I'm already 1 minute past. But you can see that it's completely combinatorial. You have points in M that have to satisfy some combinatorial condition. And the second example I was going to show you before, which I did not show you, so I will not show it again, but it's this divisor with those coefficients, something very explicit, is indeed an example of a variety that has Cohen-Macaulay singularities, has Dubois singularities, but does not have rational singularities. So it's the limit, or where you are Cohen-Macaulay, you are Dubois, but you're not rational singularities. And with this example that I never explained, I finish my talk. Thank you very much.
Thank you very much, Alvaro. Are there any questions or comments? In the people that is online, are there any questions or comments? Don't see the people. No.
Marcelo, I do have a question.
Please, Thais.
Maybe a naive question, but I would like to know, Alvaro, if because we do have, as you explained, we do have a action from a torus, and I would like to know if the orbits from this action is if there is some nice structure, for instance, if it is a witness stratification of the variety, something like that.
Okay, I perfectly understood the question. I wish you hadn't asked it. It's actually the one thing we cannot do. So she asked whether, so if you know some toric geometry, there is one thing that is maybe the second chapter in the book, which is called the orbit cone correspondence, which says when you have this picture, so are you, yeah, when you have this picture, you can read some information about the torus action from this picture. So this corresponds to a fixed point, this corresponds to a fixed point, and this corresponds to a fixed point. Technology doesn't want to work for me anymore. And then the rays, they correspond to one-dimensional orbits, and then the zero-dimensional stuff, which is the only one I see is this one, corresponds to two-dimensional orbits. So you can read the orbits of the torus action from this picture. And I guess she realized that in this part, I never put orbit cone correspondence, and it's because we don't have it. It's really complicated to actually see the orbits of the torus action from the combinatorial data the way we have it. But we can do it only in complexity 1. So there is some kind of it. So the answer is there is some kind of orbit cone correspondence, but it's not as satisfactory as we would like to, or as it is in the toric case. I don't know.
Okay. Okay. Thank you.
Thank you very much.
Are there any questions or comments, suggestions? No? So let's thank you, the speaker
Thank you
again.
very much. Picture.
Yeah.
Conference picture now.
Oh, yes, we have the picture now, okay, of the group. I forgot to say. Hello, people that is online. We are going to take the picture with you in the blackboard here, okay? Please stay there. Don't go for the lunch. Wait for 5 minutes. Hello to you. I didn't say hello to you before.
Oi, Marcelo.
Nice to see you. You should be here.
Miss
You,
Yeah.
Thais, Michelle,
Yeah.
everybody should be here, okay?
I hope that I can be able to be there next time.
Great. Very nice. Everybody hope. Okay. You don't see us, but we are seeing you, and you are going to appear in the picture. Okay, please stay there and take the mascara off, Paulo. Please, you are in. I don't know if you are in a public place or not, but if you can, it's better. Thank you very much.
A foto vai ser agora. Pode ligar a câmera de vocês, que a gente está se preparando aqui. we take the picture already. Is everything great?
Thank you.
So, bye.
Bye.
Until next time.
Thank you. See you.
Thank you. Bye bye.
Tchau, tchau, Thaís.
See you soon.